Yeah, maybe we can start now. So, could you please confirm if I'm audible? Okay, okay, yeah, thanks. So, welcome to the live session for the course Semiconductor Device Modeling and Simulation. So, today is a summary session for the whole course. So, the scheduled 12 lectures, that week 12 lectures, we have already completed yesterday, and today I'll be going through some of the important questions and some of the problems that might help you in getting, some idea about the examination part. And it might help you. I'm not also sure how will be the exam, but yeah, try to give you some ideas about what are the important topics and all. So yeah, so this is the whole course that we have covered. So I'll go maybe week by week. So initially, let me just mark some of the few topics that I feel uh, are more on the important side as compared to the others. So from week one, like week one was a very basic of this course. So we covered about the very basic of the material sense. We just saw some of the devices that can be made. We only get to know about the idea that first of all why we are only using the silicon, and again what is the crystal structure of silicon, why is it so stable, and why everything is running by silicon only. So I feel that the structure problems in which we covered some of the Miller indices and the FCC BCC, those problems might be there because those are the only numerical problems that you can get from this particular week. So yeah, I'd recommend that this part you should go through very thoroughly. Similarly, for week two, again we continued for the Miller indices and we went to reciprocal space. That is not very important, but yeah, the main thing that we got to know in this lecture is the doping part, because the conduction is because of the doping. We do not get anything out of the undoped semiconductors because they are like a intrinsic semiconductor only. So the most important topic I would say is the band structure. If you know how to make a band diagram of any device, then you know about the physics of the device. You do not need to learn any formulas. You can just by the physics of those devices you can reach to any conclusion if you know how to make a band diagram. Like if you can imagine that there is a p-n junction and how the band will bend, is it going up, is it going down, that will be sufficient. So you'll see that what is the voltage applied, and also the most important topic in the week two is the band structure, and then yeah, effective mass is again important because we also covered some of the quantum transport models in which the electron acts like a particle with some effective mass. That is a semi-classical models. Then yeah, so see, week three to six are like the most important part because we covered all the devices and all the concepts behind those. So I'd recommend for week three to six, I'll go in the problems later. So I'll show you maybe one by one each of the PPTs that we have already covered. But yeah, week three, see, density of states is very important. You need to see how the mobility of the electrons, then this Fermi direct distribution function, and the concentration. So each problem involves these four words. That this is a semiconductor having some concentration with the mobility of this, and it follows a Fermi direct distribution. So you can find the conduction band, the distance between the conduction and the valence band, or not the valence, but the Fermi level, then the distance between the intrinsic level and the Fermi level. So yeah, all of these kinds of problems comes under week three, and it is very important. Then again, week four, it was more, yeah, and then again, week four, it was more on we started with the devices. There's some noise. Could you please mute yourself? Yeah. So then week four we went towards the devices. So PN junction is, yeah, it is a very important device because that is the first device from where we get to see that how the bend like for our end side of the PN junction the bend will go down. Why? Because we have a electron flow of the from the higher Fermi level to a lower Fermi level that we are all aware of now. Then there is the IV relation, that is a diode equation that is very basic. That is the exponential relation that we have. So we also covered this. Then the minority carriers, the non-idealities. So non-idealities include the eta factor that we have, eta VT, if you remember. And yeah, these are some of the important topics. And then see, BJT is not very popular currently because BJT is a high area consuming device because of its structure. So most of the, everything that is made up of, or everything the main course that has been taught up is out of the MOS structures. MOS is a metal oxide semiconductors. Could you please mute yourself, whosoever it is? I can hear some noise. Yeah, I mean, yeah, BJT could come, but yeah, I don't feel it is very important. It is of very important magnitude. But yeah, you should see what is the Abort small model. We did cover the very basic that how those two diodes are acting like a BJT. So that is a very basic version of that. Then we see the Gamalpoon model. I mean, I'm talking about in terms of the course outline. So in the course lectures, the professor has taught about all these models. But yeah, I can say it is not very important, but the important part comes about the semiconductor contacts. So we covered about the Schottky and the ohmic contacts, that whenever the metal work function is greater than that of a semiconductor, and there can be few here and there conditions that either it is a p-type semiconductor or n type, so we can see that what kind of a contact it is. So yeah, that is some important topics, because as you might have seen in the previous lecture, the contacts that we were making around the MOSFET, let's say we try to make a contact from the source. So source is always very highly doped, because what we do not want a very high difference in the doping around the contact. So if we dope the source highly, it is almost equal to that of metal. So the contact that we apply is always of metal. So if we don't have much doping difference, then it will act like a ohmic contact. That is what we want. We do not want any barriers to come in between, whether whenever we are giving out some voltages. So yeah, you need to be aware of the concept. No formulas, nothing. Then yeah, so yeah, I'd say that the most important lecture was the week 6 in the whole course, because in this we covered the MOS capacitor, and we saw the MOS band diagram and the CV characteristics. And if you get the idea from this, then I mean, currently also, I mean, in the phones there are devices that are having some MOSFETs. I mean, um, yeah, more or less they are now having FinFETs and nanosheets. But yeah, the concept, if you know about how the physics of the MOSFET works, then yeah, that is sufficient. Then yeah, there are some important terms such as what is threshold voltage, what are the charges, what can it do if there are some interface trap charges, then gradual channel approximation, then the non-idealities. Yeah, so these are all important. So till week 6, we covered almost everything about the physics of the devices and what kind of devices we are going to deal with. And then after covering half of the course, we ran towards some modeling, or the models that we can have in the. So models are basically the mathematical part of it. So they were kind of related with all the concepts that we have studied in the above lecture. So now giving them some mathematical representation was the modeling aspect. So for instance, we started with the semi-classical transport theory. So you again see there is a distribution function, which is again Fermi-Dirac, that we already seen that what is the maths of the Fermi-Dirac function. And then again, there were this Boltzmann transport equations, that is the partial differential equations that are getting solved. Then again, mobility and scattering comes. So what are the mobility and the scattering models that we have? And then this week 8 and 9, we did cover drift diffusion models, and we also covered the derivations for the continuity equation using these. So those were very important, because there were many, if you remember, there were many special cases also that were present, that such as if the device is in steady state, if the device does not have any light, or if the device does not have any concentration gradient, how it could end up, or what is the solution to that. So basically, all this mathematics is a modeling part. I mean, you should know that how is the drift and diffusion happening, rather than knowing about the mathematics. I mean, yeah, mathematics is a plus, but physics is the main part. So if you know that this is how the drift part is happening on applying an electric field, the diffusion part is happening due to the concentration gradient. So that is enough. I mean, and with the derivation, that what are the special cases, and at least try to remember the solutions for those special cases, because a question might come up that we are having silicon at a steady state and no concentration gradient is there. So if you should know that what is the what is the relation for the minority carrier transport or minority carrier concentration for that particular case, because there were few problems also in the assignments. So yeah. Then yeah, hydrodynamic, we kind of did not cover, because yeah, again the mathematics is very complex. But the main part here is you should know that there are complex models only, and yeah, we are going deeper into that. So the mathematics again is not very important for this week 10, as I mean as per the week 10. But yeah, there are various different phenomena involved, and the lesser the size of the device, the lesser, oh sorry, the more is the complexity. So again, you should know that there are, yeah, some models, something like that. And then quantum transfer model is more or less the Schrodinger part. So we did cover it. We did cover the Schrodinger equation for even the 1D box, if you remember. Then we tried to have some of the ideas about that, how does electron move inside a barrier or inside a potential well in which we have infinite barriers, something like that. So we did cover few problems regarding that, and yeah, and then in the yesterday's lecture we end up getting this particular flow. We saw that how it actually happens inside a simulation software. So I showed you some of the snapshot for the TGAD. If you, I hope you have already watched that lecture. So we had initially we had some structure device editor in which we are actually making the device. Then once we are making the device, we are kind of meshing the device. So at every intersection point, there is this equations that are getting solved. That means there are these models which are getting solved, and we are getting a particular current value or the capacitance value on the applied voltage. So yeah, those this is kind of the summary of this course. So, I mean, the flow should be very. I mean, it should be clear now that this is how it happens, and yeah, this is how the real world devices look like. So I mean, is this summary clear? Then we can go to week by week important questions. Is it fine? Yeah. Okay. So let's see. So we have around. So first week, as I told you that we had this more on the less this crystal structure, unit cell, and mirror indices. So yeah, initially we did get the idea of what is compact modeling and all, and yeah, I maybe made aware that what is compact modeling and why do we want it and why it is even difficult, and what kind of current technology that we have, and what kind of different models there are existing in the current scenario. So yeah, so why silicon and all, but the main part, if I would say, was the crystal structures problem. Maybe if there is, yeah. So there were several crystal structure problems. So such as this, so it has crystal X, which is a diamond lattice. So it is a silicon lattice only. So you should be aware of that. Once you see the diamond lattice, you should be knowing that what kind of what is the atomic mass of it, not the atomic mass, but the structure. Like what is the number of atoms at the face, what is the number of atoms at the corners, is there any atoms inside the body? For instance, for the body centered, we have a atom at the center and at all the corners, right? For face centered, we have at every face also we have half of the atom because it is shared by face to face. So so using this, we did cover certain problems, number of atoms per cell. We calculated the mass and the density. So this is the main part. I mean, there could be problems from the density, like what are the atoms per cell? I mean, what is the density? So density is nothing but whatever atoms are there in a cell and the mass of that atom. So that kinds of adding up like a volume divided by the actual volume of the cube. So using this, we try to find out some of the density problems. So we did it for different types of crystals. So one was FCC, one was diamond cubic, and this one was BCC. So yeah, you should be knowing about these. I mean, this should be written in your mind that just by looking at, oh, it is BCC, so the number of atoms per unit cell is nothing but two. So you should, like, it should hit your mind as soon as you see BCC. Similarly, if you see FCC, it should hit your mind that it's 4 or something like that. Then, yeah, density formula is again very basic. So, volume of the cell by volume of the, sorry, volume of the atoms by volume of the cell is nothing but the density. That this is the part or this is the percentage that is being covered by the actual cell. So, again, yeah, these are all straight away problems. Then there were Miller indices. So, I told you again, so this is kind of a good criteria to find or to have some certain planes in the devices. So you should take a good look around this Miller indices part. Yeah, I mean these two are the main important topics. I guess this is the mostly we covered. Then we did cover a silicon problem. So again, silicon is a diamond lattice only. So yeah, that is fine. Yeah, so this is more or less the important part from week one. Let's move to week two. Yeah, so week two. the summary of the previous lecture was this, that we have read about the direct lattice or the Miller indices and what are the different kinds of combination. Then we went into the reciprocal lattice. So not very important, but yeah, this is one kind of some other kind of a representation to represent the metal. Oh, sorry, not metal, but the atom. So yeah, we did cover some of the mathematical problems related to that, and then we see now how this different atoms are kind of bonding and how it is leading to the different bands. So I told you about the idea. So yeah, it is a very important thing that from the atoms how we are getting those bands. So if you remember that this is a molecular orbital theory, once the atoms comes close to each other, they kind of form attraction and a repelling energy because of the neutrons and sorry, because of the electrons in the nucleus and the protons in the shells, or the other way around, sorry, the proton in the nucleus and the electrons in the shells. So this is how the band splitting takes place, and this is how we have the formation of energy bands. So we did cover this particular this particular plot in which it is how whatever the function of the distance between those two atoms is covered by the energy. So this is how we came to know that this is how the actual energy band diagram looks like. And for our simplicity, we kind of flatten it. Oh, sorry, for our simplicity we kind of flatten it, and this is how it actually, I mean, this is how we actually denote it, but in reality it is something very complex which is looking like this. So yeah, I mean, this should be very clear to you now. And then what is silicon and what are the different types of semiconductor. Yeah, so here comes all the what to say, all the minute problems, all the very basic problems, such as you know that the for a ideal semiconductor, that is a intrinsic semiconductor, the at equilibrium, the number of holes should be numbers of electrons to make it neutral. So again, this is a mass action law. This is a very important law which only holds at equilibrium, first of all. So yeah, these are some straight away problems. I guess we did not cover about the energy levels in this particular lecture because it was more about the how the band diagrams are made. So yeah, we only covered mostly about the mass action law problems in this particular lecture, and we did see what is the effective mass. So yeah, one of the more important topics was again the effective mass and how the slope of the EK band diagrams determine with that which is having a higher mobility and which is having lesser mobility. So actually it is like this, but we make it like this. So I mean, yeah, this is far or more clear. I mean, I have told you again and again this. And then yeah, there were some what to say this uh, Schrodinger equation problems, because again the solution to this only gives you the density of states. So yeah, this is kind of some intermediate topic, so that was not a very good flow to teach, but yeah, this is like it, only the course content was like this. So I need to give some idea about this Schrodinger equation, but yeah, so you should be very quick now. So you see, I mean, this problem only. So you see the what this is this the intrinsic or the Fermi level. Let's say this is the Fermi. It is very close to the valence band. So it is now very clear that this is a p-type semiconductor and all. So this is, I mean, these are all the basic things that you have got through with the initial weeks. Then we went towards wait. Then we went towards, where is week three? Yeah, here. We went towards the more of the mathematics, that what is the density of states, what is the mobility, what is how does the electron look like, or what is the distribution of electron in a device. So yeah, we started with electric field. What is this? Then there is two types of velocity. One can be thermal, which is due to the temperature. Basically, if you heat a device, there will be scattering. So due to which the electron can move randomly or the atoms can move randomly. Then if you apply some electric field, there will be some movement. So again, there will be some acceleration, deceleration, which leads to a velocity known as the drift velocity. So we covered the concept that why it is velocity and not even acceleration, because of the constant collisions, and also there was some constant velocity that was coming out. So yeah, these are all the things, and yeah, we did cover all it in very detail. And then yeah, so there were problems around the mobility, that why does it saturate? So it cannot go beyond the, I mean, we cannot increase the velocity beyond the thermal velocity, because that is a bottleneck, or that is the limit of the electron that it can move. Otherwise, it will just you can say it will just burst or it will just release some kind of energy and it will not work after that. So we did some problems which is very basic, that how is electric field V by L and mobility when, so we did different cases. If the electric field is more than the critical field, then we have some saturated case that the velocity will be always saturation velocity. And if it is less than that of critical electric field, then we have that VD equals to mu relation that holds. Then we see some of the current density part. So again, that is nothing but kind of a Ohm's law, which is J is equals to sigma E. So this is a Ohm's law in which the conductivity is nothing but the movement of the electrons and multiplied by the electric field was giving you the current. So we did some of the very basic problems from the Ohm's law also. And then we started with that Fermi Dirac. What is exactly is Fermi Dirac and what is the mathematical representation of that? So yeah, more or less we covered a lot of problems and yeah, so we did find some of the differences between the Fermi level and the intrinsic. Similarly, we can also find the differences between the conduction band and the Fermi. So yeah, this lecture, yeah, these formulas, that is what I'm talking about. This should be in your mind. I mean, not in your mind. You should know physics wise also that why these formulas are coming up and wherever there is a minus sign. So you see here N and here there is NC. So till now you should know by just seeing that NC, we know that it is greater than N for any non-degenerate semiconductor. That is what we have read in the course. So as soon as you know this, because this is greater than this, so this term should be less than 1, right? Then only this term exponential will hold. And this term will be less than 1. So conduction band is always above than that of the Fermi, right? So this term should be exponential, something negative to make it. So that is how you can even learn the signs. So if you just make it plus, you will get confused and the answer will not come in your problem. So you should be very, I mean, you should be very smart in learning these. It is not like that you can, uh, I don't know what is the term, ratta ho jayega to, yeah, it is not like that. So you need to have the idea that this maybe I'll tell you something easier, that this Ni relations maybe I'll having. I don't have the Ni relations, but or maybe I can write somewhere. So if you remember, we have this Ni relation that it is exponential of EF minus EI over KT. So now you know that this intrinsic concentration is less than that of the n, right? So this particular relation will only hold that if this value will be greater than that of 1 or this exponential term will be positive. So we know that for an n-type semiconductor, the Fermi level is greater than that of the intrinsic Fermi. So then only this relation will hold. So this is how you can see. I mean, you can also see the physics that Fermi level is above. That is why we are getting a higher or the n type of doping in the semiconductor. So all these formulas are not only formulas, but the physics also is inside them. So it is more on the physics side. If you know the physics, then these formulas are nothing. You don't need to remember anything. So yeah, there was some effective mass problems, but yeah, that is not much important. But yeah, again, so this is something similar. Then we went towards week 4. Yeah, which was the first device, that is a PN junction. Once again. So for week 4 and 5, we mostly covered the PN junction part. For week 4, we covered the PN junction and first of all the bending, how it bends if we have two different types of semiconductor. Uh, what to say? If you have two different semiconductor bars close to each other, how does the band diagram look? So I hope you remember that there are never two bars, but there is a single bar in which one side we dope it with the P type of impurities, and the second side we dope it with the N types of impurity. So yeah, these are some of the physical terms, like what is the work function, what is the electron affinity. You should know about, I mean, till this is very, I mean, these are very generic terms for you now because we have seen so many times, so many problems how the band bends. So this is a very important what to say diagram. You should see that the Fermi levels always move from sorry, the electrons always move from a higher Fermi level to a lower Fermi level, and using this you can make any band diagram. So if you even see some very very threatening looking device in your exams, such as n plus, it says n minus, it says n minus minus, then it says p, suddenly p plus plus plus, something like that. So you can like make this Venn diagram in seconds, because you know that which part will be on the upper side, which part will be on the lower side. I hope it makes sense, because this is the most important criteria that you should know, be you should know that how we can make a Venn diagram out of any device. And then this is the, I mean, holy grail of this course, that Poisson equation. This is what we are solving in the simulators also. That is, at each and every point we are trying to get a potential distribution, electric field distribution, or some current value. So all of this is coming out of this solution of the Poisson and the Schrodinger equation. So yeah, this is very important in terms of, I mean, future. You can say that Poisson equation is everything in a semiconductor. Then yeah, then we see about the PN junction. I mean, I already told you about that in the band bending, but yeah, we see how it works, what is the diffusion part of it, and what are the different formulas. So I kind of did the derivation, and then we did some numericals about the built-in voltage and all. So yeah, these are all straightforward. And then yeah, from the Poisson equation, we started with the charge density, and we then find out about the electric field. Then we find out the voltage by just integrating them one by one. So we were able to summarize, I guess, with the diagram. Maybe yeah, here. So this is what to say. This is a constant charge density at the PNN side. So once you integrate it, it will be something linear. So the integration of the constant is a linear. The integration of x is x square. So this is how we got the electric field, which is linear on PNN side. Then we got the parabolic or the quadratic relation with the potential, that is for both the sides. And yeah, this was the basic summary of PN junction. And using this, we got to know the maximum electric field is at the center, that is at the depletion region that we have. And using this, we also derived some formulas. This is this equality, that the overall xp times n is on the right side is equals to the xn times nd on the left side. Then the maximum electric field we also found, I guess. Maybe in some problem I would have. Then we also see this homo junctions, that is, it is not PR or N, it is the N plus. So I hope you can now make a N plus N band diagram, right? So can anyone, I mean, tell that which part will be on the above side or which part will be on the lower side for a N plus N case? I mean, just to refresh your memory if you want. Otherwise, I can keep on saying. No. So the Fermi level for N plus will be above, right? Yeah. What about the bands? The band will be bent down towards the N plus or N. Yeah, the flow will be there. So which part will go down? That is what I'm asking. So you see the electrons have went from this Fermi level, has went from here to, yeah, this Fermi level has basically gone from here actual place to here. So this will go down, right? So this is how it looked like, if you remember. Then similarly for P plus, I guess we did some in the next lecture or something like that. Yeah, and all the problems that we covered, I guess, also in the next lecture. So let me go there. Like five, yeah. Yeah, so yes, here's the case for P minus P we did. So P minus means, okay, let me just hide it. So P minus means where is the Fermi level? Close to valence or far from valence? Okay, no. So P minus means that it is less doped than the P. So less doped means far from the valence band. So this will be, let's say this is the valence band. So the P minus will be somewhere here and the P1 will be somewhere here. So the electron flow from here to here. So this part will go down, right? So this is how we have made. So this part have went down and all, like, yeah. And we covered the most basic thing, that BVI, if you remember, for a PN junction was KT ln NA ND over NI square, right? But when we were doing for, let's say, homo junctions, what we got to know that VBI is nothing but Kt times Ln, whatever the semiconductor that is having the higher doping comes above, sorry, and whatever the semiconductor doping which is having a lesser just comes down. So there is no involvement of the intrinsic level. Similarly, for P type, we see Na1 by Na2, something like that. That is here, right? And then we did some biasing. So till now, we were only talking about the equilibrium part. Now we applied some voltages, so we started with the reverse because that is a more important concept, that once we have more negative charges here, so this P will, like, the holes will come here, so there will be a larger depletion width as compared to the actual case. Similarly, if we apply some forward bias, there will be a lesser depletion region. So yeah, we did some. So here first we see that there are two different Fermi levels. That is a quasi Fermi level. Till now we are seeing a straight line because we were in equilibrium, but then we went towards the application of the voltage. That difference is basically the applied reverse voltage. I mean, that is due to the applied reverse voltage. And we just see that the whole formulas that we have read till now, they have just changed from VBI plus VR, from VBI to VBI plus VR, and yeah, everything remains the same. And then we see the capacitances, because it is nothing like two metal plates having some positive charge at one end and some negative charge at the other. So it is like a capacitor only. So we did see what is the junction capacitance, and then we see about the forward doping also. And yeah, these are all the same. And this is how we went towards the ideal diode equation. I mean, the whole derivation I might not have done, but yeah, these are more or less the important parts. And then again, the numerical problems. These are quite straightforward because most of them are basically related to this ideal diode equation only, or the non-ideal also will work because there will be only a eta, nothing else. Yeah, I hope you are able to see that even once you see the device that you have these band diagrams, you will be able to calculate the electric field, the current, the voltage. I hope this is what you can do now. I'm not sure, but yeah, this is what I tried to make you understand during the lectures. So we did cover some of the BJT part, but yeah, I don't consider it much important. And then yeah, these problems are very straightforward. So you can take a look again. These all PPTs are already in the drive folder. So then we moved towards the most important lecture, as I said. So week 6 was the most important lecture because we covered the MOS capacitor here. So this was very, very important, I would say. So you should even see the video again for the week 6 if you have some loss of concepts, or you are not like properly aware, or you are not able to think just by seeing the device that this is how it looks. So you should see this particular lecture again. I'd recommend that. So we covered the MOS capacitor in this, that how it looks, and ideally a capacitor should be some constant, but once we add some semiconductor in between it, this is how it acts like, and we see that why this capacitance is decreasing once we go from, if you know the technical term, accumulation to depletion. So do you remember all these things? Sorry? Yeah. Yes, yes. So, I mean, you should know that why this capacitor is looking like this U-shaped capacitor, because the decrease in the capacitor is because it goes into depletion. So it acts like two capacitor in series that makes its overall decrease. And then in inversion, again, we have an inverted capacitor that makes it again equals to C oxide for the ideal case. I mean, this is what I want you to know. More on the physics side, there is nothing in the mathematics. So if you know that how the device is working physically, how the electron, once you apply a negative voltage, all the holes in the p substrate comes near to the surface, so that makes it a oxide capacitor. And then once you apply more and more positive voltage, so the minority electrons get stuck at the surface. That is, maybe I can show you, that makes the depletion width something like this. Yeah, and this is how we are end up with the two capacitor here, and this is why the capacitor went down. That is what we have seen. And then a very high voltage will lead to the inversion of the, that is, the more electron will come out. And from this band diagram, we came to know that the p type substrate, here you see the Fermi level is lower than that of the intrinsic. But once we apply certain voltage, this Fermi level is now, sorry, this intrinsic level is now down that of the Fermi level. So this is what is an inversion of the semiconductor. It became N type from P type. So that is how that CV looked like this. Yeah, this is, I mean, this is, I have explained, I guess, very thoroughly. And what is the threshold voltage? So yeah, I will seriously recommend to watch all of you this particular lecture. That would be good for your concepts also. And yeah, so we did some of the problems, I guess, what is surface potential, and yeah, I guess there are straight problems only. So using these, so these could come that there is a CV. What is oxide capacitance? So can you tell what is oxide capacitance using this quickly? No. What is the oxide capacitance for this? From this, what should be the oxide capacitance of this particular MOSFET? What? 0.38 plus 1.15? I mean, what is the logic? Anyone else? The oxide capacitance should be. Okay, again, I'm asking what is the oxide capacitance? C ox. Yeah, what is that value? Can you tell the value from this particular figure? You understood this diagram, right? Where is that? No, I hope you are able to. So you can see the lecture again. So this is the oxide capacitance. That is the maximum capacitance. And then it decreases once it enters into the depletion. Here the series capacitance comes into the picture. Oops, sorry. Yeah. So the oxide capacitance there was 1.1 microfarad, I guess. Yeah. So this is the oxide capacitance. It is happening. Hmm. Then we do some of the circuit problems. I mean, if we ground gate and source, what could happen? So these are all straightforward. I mean, I did try to explain the IDVD equations in the further lectures, but yeah, there was this topic also in which we got to see that what is the logic, or how does a, let's say, if you want, so you must have read about the digital electronics. There are gates, and gate, not NAND gate. So how can we make it using the CMOS logic? So we did see them also in this particular lecture. So yeah, this lecture is quite important from that perspective also. And then again, some of the CV problems. Yeah. So this is the most important. Then seven is where? Yeah, here. So seven, we did some of the, again, the distribution. So now you see, you will kind of get the repeat of this course again, using the more of the on the mathematics side. So yeah, we did start with a MOSFET problem to make you familiarize again, and then I guess where is that? So yeah, this is a depletion, high frequency, low frequency. We also covered. What is the effect of body bias on the MOSFET? We also covered. That is good. So you can watch six and seven both, maybe that is more or less same. Then we went towards the distribution function. So we again see now the Fermi, what is Fermi, and how does the distribution look like. So yeah, this is what we covered. That more the temperature, more it goes away, or more is the probability of having electrons in the conduction band. And yeah, so there were problems related to quasi Fermi levels. Yeah, these are all straightforward again, I'd say. That is fine. Then we see, yeah, some of the mobility and the scattering model. So if you have two different mobilities, and what is the effective mobility, what is the effect of mobility if there is a impurity scattering, or what is the effect of mobility if there is a scattering due to the lattice vibrations. So we came to know that one increases with temperature and one decreases with temperature, and ideally this is what it looks if we do the log of that. So at lower temperatures this particular thing is dominant, at higher temperature this particular thing is dominant. And what is the effective mobility? So this is Mathesian rule. I hope you remember this also. I mean, somewhere it should be written in the PPT. That is fine. Then yeah, we see some of the donor level and all. Yeah, these are all straightforward, I guess. What else we did? Yeah, some of the effective mobility problems only. That is what we did in this lecture. and then we went towards the more on the mathematics side. So maybe week 8 is somewhere, yeah, here. Yeah, then in these two subsequent lectures we covered the drift diffusion model. So that is, I mean, it was a complex part, yeah, but I did try to go through the derivation to make you understand more that how does the drift part comes, how does the diffusion part comes for both N and P type. So this is the drift part due to both N and P. Then there is a diffusion part also. So I covered the diffusion derivation also. I think, yeah, I did cover that. And then we came to know that this is the diffusion part for N and P, and then the total will be Jp plus J, and the overall total density for a device. We covered the Einstein relation also, which is very important to solve some of the problems. Yesterday also we solved one of the problems using this, in which we find did the rho to be something like 2. We I don't know what was that, but something like this was the answer. So yeah, this is again very important. Then yeah, we also covered the generation and recombination model. So there is single atom generation recombination. There is multiple atom. So single atoms involve some basic electron hole pair formation. Then there are SRH auger recombination that are due to some intermediate play between the exciton. So we did cover that also. So if you want to see, so there is this band to band direct recombination. So it is direct, indirect also. So this was the direct one. Then there is this impact ionization one, which is the avalanche recombination. So, oh, sorry, which is the auger recombination that we covered. Then we see about the mathematics of it, and I guess we did not start to do the derivation in this lecture, and then we started to do the derivation in the next lecture because it was quite long. So maybe I can go to 9. Yeah. So we did the derivation here. So this is the recombination rate and all. So we did cover the continuity equation, and yeah, it was very long, and we came to know that this is a continuity equation for electrons, and similarly this was for holes also. You can basically derive. So then yeah, these are the very important. Now I'd say that these three cases when we covered, so for each and every semiconductor we have three approximations. There is no electric field equilibrium concentration, do not change, low level injection, but we did cover three special cases. One was the steady state and no light, using which we have this relation into the picture. Then we covered the no concentration gradient, no light, using which this is the relation that we have. Then we covered steady state and no concentration gradient, using which we have the very straight away this relation. So yeah, these three. So you can just see the problem, whatever word you see. So there can be either steady state, no concentration gradient. There can be either no concentration gradient, no light, and there can be either this steady state and no light. So whatever you see, you should know that this is how the solution of the minority carriers will look like. So for this, where it did it go? Yeah. For the first one, it will look like this. For the second one, it will look like this. For the third one, it will look like this, which is very easy. So yeah, we did problems for the same. So for the first case, we did a problem. For the second case also, I guess we did some problem. Yeah, and all. Yeah, and then we did some more of the recombination through exciton. So this is the SRH model. Yeah, I mean yeah, this is again all in all. So some of the intensity problems are also there. So this comes under optoelectronics. So we did cover this in the some of the next lectures. I don't know which lecture. Maybe in the week 10 only we covered. So this was also a concept that I covered. That is the loss of the intensity of the light. So maybe I can go there. Week 10. Yeah, hydrodynamic model I did not cover. If you really want to see the mathematics, you can go through the lectures. But again, maybe they'll be very time consuming. So it all depends upon you. So the optical absorption, we studied that if there is a light that is passing through it, there is some light that is getting absorbed in this. There is some light that is transmitting. There is some light that is getting reflected back. So how all these concepts comes into the picture and what is the power and all. And we did some of the numericals also. Yeah, I mean, these are all straight away what is the generation rate and all. So you can just, I mean, here you can understand. So this was a very important problem, I guess, some gate problem that I tried to explain in a good way so that you can get a good idea about this. What can I say? This optoelectronics topic that some is getting absorbed, some is getting reflected in this particular problem, and yeah. So this was a very good problem. You can take a look at this again. and then we see some of the MOSFET concepts, such as we have the IDVD equation. What is the transconductance? What is okay? Wait, yeah. What is the transconductance? What is the output conductance? So I hope you know that transconductance comes from the IDVG curve. From now, I mean, this is the IDVG. Oh, not very good. Something like this is the IDVG, where this is the VT. The differentiation of this is looks something like this, something like this. So this is the GMVG. Similarly, we have IDVD, if you remember, which is looking something like this. IDVD, VD, sorry. And the differentiation of this is GDS, which is the output conductance, which looks something like this. I mean, for different gate voltage, it will look something like this. Not a very good drawing, but yeah, I hope you understand now that it will increase by the slope and then it will saturate. Then we covered some of the numericals regarding this IDVD only, and some of the straight away problems regarding the hydrodynamics. So I did try to cover the hydrodynamic model in respect to the problems because they are very straightforward. So I did not go into the mathematics. So yeah, for mathematics you can take a look maybe more in the lectures. Then this some important scattering part, that what is a kind of model that a semiconductor is following based upon the length. So if the length is less than that of this coherence length and the what to say, the free mean wavelength, then it is a diffusive transport. When it is classical, when it is quantum, when it is ballistic, when it is, so ballistic is in a single direction like a bullet. As the name suggests, ballistic means like a bullet. So yeah, we did cover some of the GM problems, I guess GM GDS. So yeah, what is the ratio and all. So yeah, these are few good problems that will that maybe help you in familiarizing with more of the concepts. Uh, yeah, and then in the last to last week we covered about the Schrodinger again. So you see, it comes to a full circle. We started with kind of this, and we kind of ended. So these are very important quantum transport models, because now in these currently what the devices that we have are in few sub nanometer, not sub nanometer, but yeah, uh, few nanometers channel length. So few nanometers means very less electrons. So it is like a quantum transport models now. It is no more like a classical approach. So again, we read, or we went in depth about the Schrodinger equation, that what is this wave function, what is the significance of the wave function squared. So it will help you in finding out the probability of electron and all. Then the operators, we see that what is a momentum operator, what is a energy operator, what is the kinetic energy operator and all. And we covered some of the problems. So we'd see that this thing cannot be a wave function because it will blow up. That is, it will be infinite at infinity. That is what we not want, because we want a normalized Schrodinger wave. Then we did the derivation for a infinite, I guess, 1D. Yeah, this is the, yeah, this here, infinite potential barrier, or this is also known as 1D infinite potential well. So there are a lot of problems in this lecture from this. So you just need to know about the formula in this. But yeah, again, you should know that this is how electron will flow, like if the n is 1. This is how the electron will travel if the n is 2. This is how the electron is traveling if the n is 3. So yeah, this is you should know. So these are all wave function, because it is like a function of, if you remember, this is nothing but sine n something something n pi x by l. So I guess we came to know that, yeah, here we came to know that this is nothing but a sinusoidal function. So for single n, it will be single. For n equals to 2, it will be like a 2 wave. 3, it will be 3. 4, it will be. So there could be some diagrammatical question that this is the how electron is passing out. What is this n value and something like that. I mean, yeah, anything can come, but yeah, these are some hints. Then the energy of the particle, it is like discretized. We came to know that for a very small length it is discrete, and if we increase it very highly, it will act like a continuous classical physics only, right? If L is very high. So this is what we concluded in this particular derivation, and then we did some of the problems considering the 1D potential well, infinite potential well. So there are, I don't know if it is covered. There are finite potential wells also, which is having very deep mathematics involved in the solution of the wave function. But yeah, you can take a look and go through in that. If there is that, I don't know. Then there were some good mathematical problems. This differentiation. differentiation and integration, you should know that. I mean, you should know the basic formulas because that will help you in solving these problems. So I remember we stuck in some problem in that day. Yeah, this. So yeah, just to say that I accidentally write this x. So the problem was a into exponential of minus x square by L square. So we were kind of not able to do this differentiation. So that is how kind of we stuck. So if you some of you did try it that later at the home, so then only you will get this particular answer if there is no x in this problem. So it was a exponential of minus x square by L square. You can see the lecture again for that. Maybe there is no x in between. So yeah, that is it. So this was, I mean, more or less from the lecture 11, and yesterday I covered the TCAT part. So I hope you have also seen that. Maybe I can quickly go through that also if you want. Hmm. So why do we need TCAT now? It is very clear that before the actual fabrication, we want that how a device will act like, and there are these very complex devices that you can even just make whatever you want like a box and see what is a current behavior, so that before actual fabrication it saves you a lot of cost. And also that is why these softwares are very critical and very important to us. We can see the trends for the length scaling, width scaling, and also you see here there are different IDVGs and different IDVDs that are there. So I guess I told you it was a nanosheet, but this was a CFET. So I mean, these are all very complex. I don't want to go deep into it. So this is a complementary FET that is that is being researched in the current scenario. So as you know, that FinFETs are there in your phone, but more or less soon nanosheets will be there. So iPhone 16 will be coming up with the nanosheet. Then the next technology that might go up is this complementary FET technology. So yeah, it's just time and time the technology changes and it saturates, and this is how the flow of the TCAT. I told you that we can initially make a device, so it is like a MOSFET. So we can make a MOSFET and then see we do the matching, and each and every matching point what is happening, the Schrodinger and Poisson equation, the diffusion equations, these are all getting solved at each and every point. So more the matching, more will be the time, but better will be the result. So there should be a trade-off in between these. And then I told you that how can you write a file? I mean, this is the syntax, that this is the input, this is the output files. This are the two contacts that you will be giving the voltage. Then these are the physical models. You just need to write the name of the models and it will work because the mathematics is already there in the parameter file. Then there is this sweep of the voltage. So it goes from 0 to whatever voltage you will write here. That is 0.8 here. Then yeah, this is the complete flow. So once you have this simulation, there will be current plots. You can find the CV plots. You can find the distribution plots such as electric field distribution, voltage distribution around that particular device. So yeah, I mean these are all the major things. And then we did try to cover again some of the basic problems as I guess in the lecture 2 or something like that. I mean, this is just to make you aware that yeah, this is what we started with and this is what we are ending. So the main thing that matters is the physics and the device, and also yeah, this is, I mean, most of it from my side. So if you have anything that you want to ask quickly, you can. Otherwise, yeah, this was kind of a summary for this particular course. I hope you liked it, and I hope it helped you in generating some interest in towards the semiconductor, and we will hope to do some research or some industry jobs in this particular area. So yeah, most of it is it from my side. So if you have any query, you can ask quickly. We have 2-3 minutes, and then uh, we can maybe stop. Uh, see, see, I don't know nothing how the paper will look like. I can just give you the idea. That is what I can, but I don't know what is the kind of paper, the what is the format. So maybe you can ask the NPTEL team only by mailing them that what is a paper look like and what will. Okay, yeah. So maybe you can check that email in which it is written that what will be the format of the paper will be, and yeah, accordingly you should study. Is it objective? Did they say? I don't know about that mail. Maybe you can just quickly take a look and see what is the kind of. Maybe I can stop the recording.